Morning in calculus class. So today I want to talk about section 4.8, Newton's method for using that as approximation, finding the root, the zeros, or the x-intercept. So one thing I just want to do first is that the proof for the formula. So how we set up the Newton's method, the formula. So let's start with the point slope form. So the point slope form, as you may notice, so point slope form back to algebra 1 is considered y minus y1. So that equals m times x minus x1. Okay, so now the things that we're using the symbol as in calculus, so y, so let's call this one it's f of x. And then y1, let's say it's f of x1. And then the slope, which is just like f prime of x1. And then times the difference of x minus x1, so this one will just keep the exact same thing. So again, and one thing that I point out earlier, so it's about the x-intercept. So the x-intercept, so that means it's always considered x comma 0. The y value, it's always 0. So as you can see that the y value is 0, so that means f of x, we can set that equal to 0. So 0 minus f of x1. So that equals f prime of x1 times the quantity of x minus x1. So now, what you need to solve right here is x, okay? So how do you isolate x by itself? So first thing that you want to do, you want to divide both sides by the derivative. So divided by f prime of x1. So it's going to be written as negative f of x1 divided by f prime of x1. So you're left with x minus x1. Again, we want to isolate x by itself, so that means we want to take negative x1 to the left-hand side. So eventually it's going to be written as x1 plus f prime, well, plus f of x1, excuse me, over f prime of x1. So that equals x. And guess what this one is? So this one is the Newton's method for doing the approximation of the x-intercept. So now, let's just rewrite it as the sequences in series. So anytime that you deal with that xn plus f of xn, so let's give that the general subscript number, so n. N is just like the term, 1, 2, 3, 4, 5, 6, 7, so on and so forth. So that just the indication of the term. So that equals x sub n plus 1. Okay, so Newton's method. So we're going to be using this one for doing the approximation for any kind of complicated functions for finding the x-intercept and also the roots. Okay, so the main purpose of using the Newton's method, solving x-intercept for any complicated functions. Second one, approximating any irrational numbers. Okay, so interesting. So we're going to do some example like this in a minute. Okay, so now to look at the next slide. So use the third approximation to find the root of the given equation. And then round the answer to the 4 decimal places. So one thing that we notice, so we started with the functions. So the given function, it's f of x. It's x to the power of 3 plus 2x minus 4. And we want to find the x-intercept for this. The root, that means the x-intercept. And for those, you might be saying that, well, this one, we can just set y equals 0 and then just do it on the calculator. Well, certainly you can do it that way. But the thing is that we need to start with the given x value. So the given x value, x1, the first approximation, is 1. So we need to start it off with that 1 right there. Again, for the Newton's method, so x n plus 1, so that equals xn. Wait, one thing that, let's go back to the previous slide right here. I think I did something wrong earlier. Yeah, this one's supposed to be minus, so this one's supposed to be negative. So let me fix the sign right here. It's not a plus, it's minus. So this one right here, so it's x1 minus, because this side right here is negative, so negative positive, so it's negative. Okay, I apologize for that. So the Newton's method is supposed to be x sub n minus f of x sub n over f prime of x sub n. So that equals x sub n plus 1. Okay, so this one, let me just rewrite it here. Minus, so f of x sub n over f prime of x sub n. Okay, so now, I'm sure that you don't want to do this manually, so you want to put it into the calculator. So let's put it into the calculator and see what happens. So let's see, graphing calculator. So go to y equal. So x to the power of 3 plus 2x minus 4. Okay, so plus 2x minus 4. So the 0 looks like we do have some zeros here. So now the next one, you want to put in that the derivative. So for those you might be wondering, how do I put in derivative for this? So you want to go to math, and then you see that number a right here. So deriv. So we're using that deriv. So that means it's the derivative of d over dx times the functions. Well, of the functions. So the function, then that would be vars, y vars function, and y1. And we're taking the derivative with respect to x. Okay, so the second function that you want to put in, it's the derivative. And now what about y3? So y3, we want to put in the Newton's method, the formula, which is x minus, okay, so the original function, that goes first, which is y1, again, vars, y vars, y1, divided by the derivative. So the derivative that we put in here is y2. So vars, y vars function, and then this time select 2. So that's y2. So that right here, y3. So this one gives you the Newton's method, the formula. So it's x minus the ratios of y1 over y2. So now, again, we're not doing this manually. We just want to use the calculator. So we want to go to second and table. And now you see that we do have 1, 2, 3, 4 columns. So let's start with the first x value. So let's see what the first x value is. So it's 1. So let's start with 1. Press 1 here. Enter. So y1, it'll give you the y1, you know, the y value. y2, it'll give you the derivative. And then y3, that's the approximation we're using. So it's 1.2. And guess what? And how many times that we need to do this kind of repetition? So we need to do the third approximation. So using the third approximation to find the root. So that means we need to do this one 3 consecutive times. So we're gonna, whatever the outcome that we have for y3, we're gonna use that, the new number, 1.2. Whatever the value that we have, we use that to find the another approximation. So 1.2. And then we came out with 1.1797. So we're going to use that, 1.1797. So as you can see that right here, those two numbers, they're getting very close. So the more approximation that you do, the better, you know, the more accurate the solution is going to be for the x-intercept. So since we're doing that, the third approximation, so the final value for the x-intercept is about 1.1795. So 1.1795, and also under the instruction, how many decimal places that we need to round? We need to round it to 4 decimal places. So it's 1.17, it's 1.180, so you need to round it up. So eventually the x-intercept, it's about 1.1780, comma 0. Okay, so let's take a look at that one more time. 1.180. 1.180, excuse me. Okay, so 1.180. Okay, so that's what we have. So now let's try the next one and see what happens. So the next one, we do have x to the power 5 minus x minus 1, so that equals 0. So it's pretty much the same thing. So back to y equal, so let me just clear off this. So y equal, we just need to change that. So this one is x to the power 5 minus x minus 1. So x to the power 5 minus x, and then minus 1. Okay, so that's the trinomial. It's a 5th-degree trinomial. So the rest of this, you don't want to change that. It's pretty much the same kind of template. So it's the first derivative. That's what we need to apply. y3, it's always the Newton's method. So now let's put it in and see what happens. So back to second table. So this time the first x value, so let's see what that is. So the first x value, which is 1. So let's just plug in 1 there. And we got 1.125, no 1.25. And now using 1.25, the second approximation, so it's 1.785. And then the third one, so 1.1785. So this number should be very close. So it's getting very close. It's 1.1675. So for the x-intercept right here, so it's 1.1675, comma 0. Okay, so check that one more time. 1.1675, comma 0. Okay, so that's just the strategies, the step that we need to go through. So to find the approximations for the x-intercept. So now let's see what else that we have. So the next one, use Newton's method to find all roots of the equation to correct to 6 decimal places. Okay, so all roots. So it's not just the one getting close to the given value, but we need to find out all roots. So first thing that you want to do, so you want to set up that y1. So y1, so this one will be considered x to the power 4 minus x minus 1. So basically just bring everything all together to one side and set equal to 0. So we do have a 4-degree trinomial. Okay, so now, so first thing that you want to do, okay, so put in the function. So we got x to the power of 4. Bring down the cursor. And let's see what else that we have. Minus x minus 1. Okay, minus x minus 1. Minus x minus 1. Again, the rest of the function, we don't change that. But one thing that you can do right here, so let's say that you want to take a look at the graph for y1 and see where the zeros are allocated. Okay, so let's just unshade those equal signs. So just go to the equal sign and then press enter. So now you're unshading them. So that means the only graph you're looking at right here is just y1. Okay, so now y1, and then go to zoom and then standard. So we just want to focus on y1 and see where the zeros are. So it looks like we got 1 here, and here's another one we have. Okay, so it looks like the first x-intercept would be considered something that's close to -1. So let's say that it's -1. Okay, so back to y equal. So now this time I need to shade the y2 and y3 because I'm going to put into the table. Okay, y2, y3. Okay, back to the graph. So -1 first. So we do have -0.8. So let's just do another approximations. So -0.8. And now this time we came up with -0.7312. Okay, one more time. -0.7312. Again, the more approximation that you do, the better the accurate the answer that's going to be. So the next one, so -0.7245. So -0.7245. Again, it's all negative. Now, is that the time you want to stop here? Well, because the number that you enter is the exact same as the one from the outcome. Okay, so that's why you want to stop here. So the first 0 would be considered -0.7245. Okay, so the first approximation, the first intercept, x-intercept would be negative 0.7245. This one you want to round it to 6 decimal places, so let's just add the 0 here. Just put the zeros, comma 0. So that's your first x-intercept. And now what about the other x-intercept? So back to the calculator. So back to the first row, first column. So it looks like the other number right here, it's getting close to 1. Okay, so let's use 1. So we got 1.33333. Use that, 1.33333. And then we got 1.2358. Okay, 1.2358. And now this one's getting very close, so it's 1.2211. Keep doing that, 1.2211. And now we got getting 1.2207. One more time, 1.2207. Again, by the time that you come up with the exact same value as the x value here, so that means you want to stop right there. And that's your x-intercept. It looks like that's the one, 1.2207. Okay, so another x-intercept, 1.2207, comma 0. Okay, so now let's see what else that we have for the rest of this. So this one you can try this. So again, so y1 for this one, you can just try that with the practice. So then that will be considered cosine of x minus x to the power of 0.5. Now, got to be careful with this. There's a trig function involved. So that means you're using the variable as radian. Okay? So let's do this one right here. This one right here is written as e to the power of arctangent, inverse of tangent of x, minus x to the power of 3 plus 1 to the power of 0.5. Again, you don't want to do down the manually. You want to do down the calculator. So that's y1. Okay, so let's do cosine of x minus x to the power of 0.5. Okay, making sure that this one, the radian, it is in radian. Okay, so we do have cosine of x minus x to the power of 0.5. Okay, so once again, second table. So the first one, it doesn't really matter. You can put in any number you want. So let's say that 0. So we got error because that would be considered undefined for the derivative. So instead of using 0, let's use something else. So let's say 0.1. So we end up with 0.5038. Okay, try that one more time. 0.5038. And then we got 0.6436. And then the next one, we got 0.64171. Okay, let's see what that is. And that's the one. So for the x-intercept, we do have 0.64171. Okay? So 0.64171, comma 0. And this one also can do that too. So e to the power of tangent, inverse of tangent. It's a little bit complicated for this one, so let's just put it in carefully. So second, base e to the power of inverse of tangent of x. So second tangent, and then x. Bring the cursor back down here. Let's see what else that involves. minus the quantity of x to the power of 3 plus 1 to the power of 0.5. That's a lot of stuff right there. Minus the quantity of x to the power of 3 plus 1 to the power of 0.5. Okay, making sure that I plug in everything correctly. That's right. Again, the first x value, educated guess. I would say maybe -1. Okay, let's try that. Any number you want. Okay, so you can use 0. Looks like it's going to be 0. That's the first x-intercept. It's going to be 0. But what about if that's -1? That's an error, so you don't want to use negative. So let's say 0.2. So we got 0.00728. Okay, plug in that number, 0.00728. And then we got 2.6 to the power of 10, 2.6 times 10 to the power of -5. It's a scientific notation. It's getting very close to 0. So let's put in that number. So 2.6 times 10 to the power of -5. It's just getting smaller and smaller, so eventually it's going to be 0. So you can say that one right there, 0, 0. Okay, so for that one. Okay, so now the last one. So this one, and you want to use the Newton's method to find the coordinate of the inflection point. Okay, again, misspelling of the curve. So e to the power of sine x. And this one, it shows the restriction, so x got to be from 0 to pi. And then you want to round the final solution to 6 decimal places. Okay, so let's see what else that we have. So this one's the last one. Okay, so now let's put in that y equals e to the power sine of x. Now this one you got to be really careful with finding the point of inflection. So back to the definition of point of inflection. So that means we need to set the second derivative equal to 0. So basically we need to find the x-intercept of the second derivative, not the original function. So this one, there are a lot more work we need to put into the graphing calculator. So let's just put in the function first. So let me just clear everything. Okay, clear. Even that, the template for y2, y3, because we need to find the second derivative. So the function that we have is e to the power of sine of x. Okay, so e to the power of sine of x. Okay, so that's what we have. So now we need to find a second derivative. So one derivative at a time. So math, 8 d over dx. Again, function, y1. We want to use that. Vars, y vars, y1 function. And then x equals x. Because that we're taking the derivative with respect to x. And now what about for y3? We need to find a second derivative. So similar process. So math, 8. And now this time, instead of using y1, we're using y2 because we're taking the derivative from the first derivative. So vars functions, y2. And then again, taking the derivative with respect to x. So x equals x. And now for the y4, this time we want to put in the Newton's method. So it's x minus, okay, so y3, which is the second derivative. So y3 okay, so then that'll be vars, y vars function, y3 divided by the derivative of y3. So the derivative of y3, so let's say this one it's math, 8 once again, d over dx, derivative of y3 function, And this time, y3. So basically, I just want to put in the Newton's method, the formula. And again, with respect to x. So y4, that's the one we need to focus on. Okay? So that's the one we need to focus on to find out the point of inflection. Again, the point of inflection is that when y3 equals 0, so we can find the x values. So that's why we're using the Newton's method for the second derivative. Okay? So now let's find out what that is. Second table. And one thing that we noticed, so the x value should be founded from 0 to pi. Okay, so there's an error here, so let's go to and see what happened. Okay, everything looks good. I think what I need to do for y4, I need to take the derivative again because that would be the derivative of y3. Okay, let me just clear this. So one more time, math, 8, y vars, function, and this time y3. Okay, but putting the derivative d over dx, and then y3. Once again, this one is a lot more complicated compared to what we just did earlier. And now for y5, so this one you want to put in the Newton's method. So again, the original function, the first derivative, second derivative, and now the third derivative, because we need to use that for the Newton's method. So it's x minus, so this one will be considered y3 over y4 divided by y vars once again, y4. So finally, y5, that's the one we need to find out. So second graph. Oh, you know what? I need to change the window. So the window. So it's getting stuck right here for the calculator. Okay, let's go to zoom and change the window. Or just go to window, go to. So 0 to pi. Okay, and then second table. Because the earlier window, so that was from -10 to 10. Well, there's something wrong in illegal nets. Let's see what happened here. Yeah, sometimes that's kind of weird, you know, for the function. Something that comes up. Okay, so e to the power of sine of x. That's what we got. Excuse me. Yeah, so try to go through that on the calculator with a similar procedure. So I think I need to reset the calculator. There's some kind of error here that I put in, I think. E to the power of sine of x, derivative. Everything is right. Derivative, y2, y3. Yeah, so try to follow through the same kind of step like what we've been doing, and you'll get to it. So it looks like there's certain thing I need to reset on the calculator here. Okay? So, and it looks like I need to put up another video like this for the last example. Okay? So I'll see you guys next time. Thank you. Bye-bye.